Okay, for the review and refine of suspension requirement for steering and suspension. Okay, designing and implementing a lightweight, responsive and robust steering and suspension system is important in for EV racing car. This is for to ensure optimal handling, stability and the driver feedback during the high dynamic tool which typical for racing environment. Okay, so in general, the requirement for both system must of course follow the racing rule and allow for quick adjustment and replacement. So these are the requirement for the suspension and steering system for EV racing car. As you can see on the table, there is the steering system requirement for the EV racing car, which it has defined the requirement ID and the requirement and the details. So for example, you can see at the table STR01 for the steering type requirement, that the detail is the rack and pinion system for the process control, and for the steering ratio is must be adjustable between 10:1 and 10 and 21. For the steering geometry, it might use true or modified Ackermann geometry, of course, and the driver feedback must provide clear and direct tactic feedback. For the steering angle, for the steering system must targeted around 35 to 45 degree per wheel, which full lock angle will gonna be at least 180 degree at steering wheel. And the clearance must have no interference with suspension or other system to full movement. The adjustability must toe and chamber adjustable, which via tie rods and joints. And the safety and the stability must have, of course, no bump steer or mechanical binding.
Assalamualaikum and greetings to all. So today I will discussing how our car suspension subsystem needs have been reviewed and improved in order to fulfill performance targets and handle the demands of an electric powertrain. So to guarantee the best possible vehicle performance, the suspension system is crucial component that needs to be careful connected with other subsystems. It must be adjusted to fit the properties of the tires we have chosen, so such as their grip levels and stiffness. Additional difficulties including torque vectoring, mechanical braking and the dynamic weight transfer that takes place during braking and acceleration must also be recommended with electric vehicle. So to satisfy these needs, we list 10 important suspension requirements. First, we went with an independent double wishbone suspension system, which provides fine control over chamber angles for improved handling and grip actions. Because the ride height is changeable, usually range from 25 to 50 mm, we can adapt to various tracks and surface conditions while still achieving a aerodynamic performance. So in order to fine-tune rebound and compression settings, we employ adjustable coilover dampers for damping. This guarantees that our configuration can be adjusted for performance or comfort based on the situation in order to maintain drive control and comfort during serious action. The suspension travel is engineered to be properly so efficient to avoid bottoming out or topping out. So to keeping the chamber gain at the proper level is also crucial. For optimal tire contact and grip, we strive to maintain the wheels correctly aligned with the road throughout the suspension's motion. We have reduced pitching during braking and acceleration by including anti-dive and anti-squat properties into the design. To better stability and driver confidence are thus guaranteed. We use advanced simulation tools like Adams, Optimum K, and Lotus to test our suspension design. Before conducting physical testing, we can use these methods to predict how the suspension will behave under different load conditions. Additionally, we built the suspension so that spring and damper adjustments would be simple. This implies that we won't need to do a lot of rework to modify the setup at the track for various situations. So the stability of the roll center is another crucial element. In order to maintain vehicle balance and cornering predictability, our design reduced the roll center's lateral displacement. Last but not least, we work to lower the unsprung mass, which enhance the tire's ability to maintain contact with the road, particularly over bumps, improving grip and reaction time. To sum up, each of these finely tuned specifications helps create a suspension system that is not only highly effective but also flexible, effective, and well suited to the particular difficulties presented by electric vehicle performance. This strategy guarantees both driver safety and competitive performance. Thank you.
Assalamualaikum and hi. So I will continue this group presentation with introduction to basic calculation. There are two basic calculation in this group topic, which is steering and suspension. So first calculation is about steering torque estimate, which is manual, which is in manual right and pinion. First of all, we assumption the first tire rod friction coefficient mu equal 0.9 in static. Second, we assumption steering angle at full lock, which is 35 degree. Third, we assumption a static front axle load, which is 60% of 300 kilogram, which is 180 kilogram, and we get the 900 Newton per wheel. So the calculation first, we find the lateral force by using the formula F equal mu times N. So we get, which is 0.9 times 900. So we get the answer is 810 Newton. Assuming 0.3 meter scrap radius, which is distant from kingpin axis to tire contact patch, we find the torque by using the formula T equal F times R, which is 810 times 0.3. So equal is 243 Newton meter at the wheel, with a typical 16:1 steering ratio. We find the steering wheel torque. So the 243 divide by 16, we get the answer is 15.2 Newton meter. This exceeds our 10 Newton meter target. Power steering or geometry optimization may be needed. Next, for the second calculation is basic suspension spring rate estimate for front suspension. First, assumption the sprung mass per front wheel, which is 75 kg. Second, desired natural frequency, which is 1.2 Hz. So by using the formula Fn equal 1 per 2 pi times square root k per m, and convert it to k equal in bracket 2 pi Fn, the power of 2 times m. So um, we we calculate and get the spring rate is 2135 Newton per meter, and the final answer is 21 0.35 Newton per millimeter.
So in this study, McPherson suspension and double wishbone suspension are chosen to be studied in this project. McPherson suspension is simple and cost more less weight and less structure to be construct for a vehicle. Double wishbone involve more component in the structure, but also provide better handling and overall performance against the McPherson suspension in most cases. So for the parameter we'll be looking for is the toe angle, the camber value, and the caster inclination again in these two suspension. So for the definition of the toe angle is the angle or the direction of the wheel when it's viewing from the top view, which the wheel is either pointing inward or pointing outward from the car. So for the camber, the positive camber is the wheel when the wheel is pointing outward when it's viewing from the front of the car, which the upper part of the wheel is inclined outward, and for the negative camber is the upper part of the wheel is pointing or getting inward, approaching to the wheel chamber. So for the kingpin, for the caster inclination is the direction of the rotating axis of the kingpin. It's either approaching near to the driver or near to the vehicle center or outward to the vehicle center.
Assalamualaikum, my name is Luman, and today we want to discuss about component inside the House of Qualities, HOQ. So for my group, we want to discuss about suspension system. Alright, so we go to the first component, is the customer requirement. Means for the question is what? So the function of the customer requirement column is we want to know what customers want and their needs. For the second one is technical requirement. The technical requirement is we want to translate what customers need based on the measurable concept. Next, we move to the relationship matrix. So the function of the relationship matrix is we want to measure how strong the customer requirement based on technical requirements concept. So we need to know the relationship between two of the requirement. Is a strong relationship or weak relationship. For the next part is correlation matrix, which mean as we can see the roof part, the shape of the roof. The function of the roof is we want to identify either the relationship have a synergy or have a conflict or doesn't have any relationship. So for the number 5 is we go to the customer important rating, which means we need to know the parts that we want to prioritize first before we move to the next function. For the function of the number 5 is the competitive benchmark. So the function is we want to identify areas of improvement and the competitive positioning. Okay, for the function of the number 6, we go to target value, which means we want to provide the engineers to target the guide development, which means we want to know what is our priority and what is our target. For the last one is difficulty rating. Alright, for this component is optional. It will help balance feasibility and effort in engineering decision, which means the relationship we want to make the progress is balanced and not too harsh. So that's all from me. Thank you.